In this video, we're going to look at topic 64, example 3, where we understand stretches and compressions. So for these two examples, A and B, everything has been worked out already, everything is written out. I'm just going to go through it through the procedure and explain what a stretch and a compression looks like and how it affects our graph. So part A, they want us to graph f of x is equal to the absolute value of x, and that's already been graphed here in blue. So f of x is equal to the absolute value of x. With domain -4, 4, you can see that here our domain has its limits. And g of x is equal to 2 times that f of x. So that is graphed in red. And they want to know how are the domains and ranges related. So one of the most straightforward ways to find some values and to compare them is to use a chart. Now you could graph these using a graphing calculator or a program like Desmos, but you don't have the chart, so you can't very clearly see where one point changes to another. So on the left column here, so we'll go column by column, we have our x values, and those are the x values that we plugged in to find f of x. So any of these values we plugged in here, the absolute value of -4 would have been 4, -2 is 2, and so on. So each of those was plugged into the function of x, or f of x. That's where these points then become our x and y coordinates to graph f of x, that blue absolute value function. Then we're going to look at g of x, and we want to compare f of x and g of x. So for g of x, what we did is we took the values, this -4, -2, 0, 2, and 4, and those are plugged in as our x values. And we still found f of -4, which we know was 4, and figured that out. And that's where these numbers come from. Function g tells us to multiply by this 2 here. So that's where we're multiplying by 2. So we're multiplying our results from f of x by the constant of 2, and you'll get your new numbers here. Those new numbers are your y values, or your g of x values, right? If we plug them from x for g of x. And then these original x values, or these x values here, are the same ones that we used right here. Okay, so we're just showing how they change. You can look at these on the left as coordinate points. And then obviously we already wrote that right column, this column here, as coordinate points. And we can compare them. Well, the x values are all the same. And that's where they state down here, the domains of f and g are the same. We have the same limitations in terms of x, right? The domain stays the same. However, each y value has been multiplied by 2. So for the function with the given domain, the range was 0, 4 for our f of x. But in g, that doubled. Now that goes from 0 all the way up to 8. Okay, so since we multiplied f of x by 2, our range is going to wind up being doubled. And more specifically, the second kind of statement here, it says a transformation that increases the distance between the points of a graph and a given line by the same factor is called a stretch. So you want to be familiar with this term here, a stretch. The graph of G is a vertical stretch. All right, and we'll get into more detail as the lessons go on the difference, what we really mean by vertical stretch. But just think of it as the graph is being kind of pulled taller. All right, we're making it longer, vertically. And again, the graph of G is a vertical stretch of the graph of f by a factor of 2. That 2 being, running out of highlighting colors here, that factor of 2 is what came from up here, that multiplied by 2. All right, so that's the basic concept of vertical stretch. There's much more detail we can go into, but right now we're just trying to use this as an introduction. In part B, we have this same kind of concept or same idea that we're trying to apply, but this time something slightly different is going to happen. And again, f of x is equal to absolute value of x. We've graphed that in blue. And I'll try and use the similar colors here. And then these numbers here, the -2, -1, 0, 1, and 2, those are the numbers that we plugged into f of x. So those numbers got plugged in right there. The f of x values, when we find the absolute value of -2, of -1, 0, 1, and so on, again, I'm just going to try and keep the colors the same. These are the results that we get. In terms of h of x, we're still looking at the same domain, but this time h of x is f of 2x. So notice before with g of x, that 2 was outside, it was 2 times f of x. This time that 2 is on the inside, it's f of 2 of x. So you'll see that that's going to make a different change to our graph. And again, they want to know how the domains and ranges are related. So we're taking our -2, -1, 0, 1, and 2. Those are still being plugged in to our function. And this time we're multiplying by our value of 2. Okay, this 2 here. They kind of skip a step in this case, or not necessarily skip a step, but when they're multiplying them, right, we do 2 times -2. Since it's inside, we do those operations first, and these are the numbers that we get when we multiply those kind of green highlighted times the blue highlighted ones. And then that number, that f of -4, will then get plugged into your f of x function. So it's a little tricky in what numbers get plugged in, but hopefully you're able to follow that along and see where these numbers come from. So these are the pink ones that we used, and then these ones are the original blue. And if you take a look at your domains and ranges, we'll talk down here. For each corresponding output, the value of the input for f is half of the value of the input. Input for h is half the value of the input for f. The two functions have the same range, right? These ranges, oh, that's not true. These ranges wind up being the same. We still go from 0 up to 4. That hasn't changed. However, our domains this time are different. The domain no longer goes from -4 to -4. It now goes from -2 to +2. So what's happened is we've cut our domain in half. And this is one of the trickier parts of dealing with functions like this, is that people see that multiplication of 2, and it kind of gets confusing as to why these numbers get smaller. Right now, just understand that this is going to be a little bit backwards, and as we get into more detail with stretches and compressions, it will start to make more sense. I wish I could say it was something very easy to explain and understand, but it's not necessarily that way. You kind of have to see some examples and just see it in practice. And as you start to work through these, you'll start to understand it a little bit better. So this second statement here, or this last statement, a transformation that decreases the distance between the points of a graph and a given line by the same factor is called a compression. So there's another key word we want to make sure we're familiar with. The graph of h is a horizontal compression of the graph of f by a factor of 2. So compressing, think of it as like kind of squishing it or making it smaller. In this case, things are being pushed towards the y-axis. So it's a horizontal compression, and think of it like a vise. It's being pushed, or a press. It's being pressed in from the left and right sides, and it's compressing it horizontally from the left and the right. So not always the easiest. Horizontal compressions are one of the least favorite things for most students. Vertical stretches tend to make a bit more sense. They're more intuitive. You can kind of see it much more clearly, but you'll get the hang of it. It'll just take a little bit of time.